Hello, everyone, and welcome. Thanks for coming to today's presentation on tips, tricks, and traps, sharing test data across the bench and into the cloud. My name is Brad Odner, and we'll be joined a little while later by Rick Coleman, and both of us are, of course, from Tektronix. Okay, here's our rough agenda for today. We're going to start out with a little bit on the need for data access. I always like to start presentations with a little bit of context around them. Then we'll talk about local access to data, sharing just straight across the bench. We'll talk about optimizing data for sharing, as well as remote access to data. And by my count, I think we have about 4 tips, 5 tricks, and 2 traps that we'll be walking through today if you want to follow along with your own notes at home. This is an interesting little historical artifact that we have at the Tektronix Museum. You know, Tektronix is turning 75 years old this year, so we're feeling a little bit nostalgic this year especially. But it's interesting to think about how not too long ago, just how difficult it was to pull data off of a piece of test instrumentation, where you might have to have a device like this, a special rig and a film camera to snap photos of your data, then have those images developed. And that was the only way you would have to record data. Of course, nowadays, there are just so many different options. We actually have somewhat of the opposite problem. Now there are just so many options. I find that many people just don't know where to start about how they should pull data off of their instrument. And of course, the data that we pull off this test instrumentation is being used in more places and in more ways than ever before. Whether that be for long-term storage, I often hear from companies that have reporting or compliance needs where they need to store data for a set amount of time. For analysis, of course, on raw data, collaboration between team members, both local and remote remote lab access. Especially important nowadays with people wanting to feel like their piece of equipment is right in front of them when it may be in a different city or a different state or even on the other side on a different continent. Uh, and all of these reasons are just becoming even more prominent, where being able to use a piece of test equipment as it sits right in front of you seems to be less and less common in favor of advanced remote access capabilities and just general collaboration between different pieces of test equipment on the bench, so that we're no longer sitting there twiddling knobs and looking at numbers straight off of a screen, but instead doing more analysis elsewhere. But enough introduction, let's get into some tips, tricks, and traps. And we're going to start off with the one that I get questions for a lot, a tip on choosing the right interface. I put together this table recently to try and help people choose the right interface if they're starting off with a piece of equipment. Now, of course, this is a very big generalization across this whole table, but I do think it holds true for probably the most common use cases, the most common instances when people think of these interfaces and hopefully these capabilities too. I'm not going to go through everything on here, but let's just talk in general about some of the key capabilities of USB, Ethernet, GPIB, and serial or RS-232. USB is becoming probably the most common remote interface nowadays. And a really great thing that it has going for it is it has fantastic transfer rate. That the data can come out of an instrument and into your computer really fast with USB. It's okay in its simplicity. Generally, you oftentimes have instrument drivers that you have to worry about, and those trip a lot of people up. We get a lot of support calls on that. And triggering is also not fantastic if you have multiple USB instruments, because USB controllers and computers are really just not designed to have a single trigger go out across multiple USB instruments. So that's something to think about. Ethernet, I generally recommend to people because I think it has the most capability, and that capability one there is a little bit cheeky, but that'll come up in a future tip on here as well, so we'll get more to that. But Ethernet has some great transfer rate. Triggering is generally okay across it, at least more consistent than USB generally. And you can get the cables for Ethernet really, really cheap, and you can even make your own. So it's also great for cost, I think, for that reason. Very hard to make your own USB cables, for example. GPIB is the most classic one, very simple to implement. Don't generally have to worry about drivers as much, at least not as much as with USB. Triggering is, GPIB was designed for test instruments, so triggering with it is pretty great. And then, of course, serial RS-232, we don't really recommend a lot. It's generally more of an older standard, pretty slow in comparison to these other interfaces, but that's not to say that it doesn't have its general use cases. It can also be fairly reliable. And of course, if you already have a test stand built for serial, then that's probably the one you should use. And hey, look at that. It's that tip that I was just talking about for LAN or Ethernet, or I suppose I should say it's really a trick, but LXI access. This is LXI in the grand scheme of things is pretty new, actually. Developed within the last 20 years or so, really started to become popular and integrated onto test instruments. But LXI access often goes by two names here at Tektronix and Keithley. It's the virtual front panel, or E-scope for Tektronix. If it's an oscilloscope, then it's known as E-scope. So let's talk about what LXI access really is. LXI stands for LAN Extensions for Instruments, and it's a standard developed by, funnily enough, the LXI Consortium for test instrumentation and how they should interact when connected to a local area network or just a LAN network. A very common thing that you'll see is the ability to control the instrument fully from a dedicated web page that it has up. So this gives you just 4 easy steps to be able to get remote access or local access to your piece of equipment. You just connect your instrument up to the LAN network, assuming it's LXI compatible. You can tell LXI compatible instruments because somewhere on them they'll have this LXI symbol that you can see off to the right. Then you just find the instrument's IP address. So like down in the bottom left here, I actually grabbed this screenshot from the LXI web page of our DMM 6500. And instruments that have LXI support will be able to report their IP address somewhere. You can see it just below the TCP IP mode setting on the DMM 6500 there. Then you just type in that IP address into your web browser and you get a whole panel of control for your instrument. So this is a great, very handy thing if you need just very simple control, or if you're also in a different area. So assuming you're not blocked by a firewall, which can be a problem for larger companies, you can get connect to an instrument really from anywhere, because as long as you're able to get to that local area network from the internet, you can connect up to your instrument no matter where you are. And we've done experiments with this. The lag can get pretty hard if you're trying to access an instrument in mainland Europe when you're in the United States, but we have done it before. And oftentimes this LXI panel is great for quick data extraction as well. So right in the middle there, you can see the settings panel from the DMM 6500 LXI panel. So you've got some administration capabilities, configuring an IP address, that virtual front panel where you can just see exactly what the instrument is seeing, send remote commands to it, as well as extract data. So in the case of the DMM 6500, what it allows you to do is just save the buffers from the instrument right onto your local computer. So LXI access is a really great trick for you to use if you are, of course, using LAN as your connection standard. Let's talk about another tip, controlling instruments with Python. I'm sure a lot of you are using Python right now. It is, after all, the most popular programming language in the world now. But, important to review some of the nice tips that go along with it. And we're also going to talk about a trap that comes along with using custom coding control of instruments, which is local file storage. Now, controlling instruments with Python, you generally need 3 things on your computer to be able to do this. You're going to need Python, of course, recommend version 3 at this point, not 2.7. You're going to need an instance of Visa and the PyVisa library. Now, strictly speaking, a separate installation of Visa is not really necessary, in theory at least. You could just use Python and PyVisa, which are both completely free for all purposes, all open source and everything. Visa is not open source, though it is generally free if you're a consumer. And with these 3 things together and some remote interface of how you're connecting up to your instrument, you can get full control of it with just a quick few simple lines like here. So here's some Python in 3.7 to import PyVisa, of course, because we're going to load that PyVisa library. we're going to set up a resource manager, which is just a quick one line, basically a code data structure to be able to manage all of your instrument connections. We're going to name a connection as Keithley. I often see people with a particular Keithley instrument that they have just calling it the Keithley. So that's what we're going to call our instrument today. Maybe it's a DMM, for example. And then we just pull data off of it with the .query and then send whatever the command is in order to be able to get data off that instrument, or have the instrument report data back to us, I should say. So that's quick, a very simple 4 lines, and now data contains the buffer from our instrument of all the data that we might like to get. So PyVisa, really fantastic, very easy to use for controlling instruments with Python. It's what we recommend. There are other solutions out there, but PyVisa does seem to be consolidating all of them, and we start to see PyVisa show up more and more. We do have some tutorials online too, the Tektronix and Keithley do, I should say, on using PyVisa. PyVisa has their own tutorials as well. We're not going to go too much further into it today, but this is a good tip for you. Now, along with the ease of using Python for instrument control and pulling data off of instruments, comes along the trap of what I'm calling local file storage. In other words, writing files onto your hard disk. And this is true not just for Python, but for any generally custom written code that you may use. So here's an example of a very simple way to write data to a file with Python. I'm not going to walk through it in detail, but you can see we're creating a file data.csv, and then we are writing our data into that file. The problem really comes in the naming of the file. So where is this data.csv file? Well, by default, just as I've written it here, it'll show up in wherever the repo is where you're executing this code, which is probably not where you want your data to actually be stored. Now, I know I'm guilty of this trap, and just sort of tap your desk, raise your hand anytime during this slide when I mention something that you've done before, whether that's saving data to a file that you didn't mean it to be saved to, and also overwriting data too. So here, let's be a little bit more thorough with our file naming convention. So I'm going to save it to a separate drive, not on my C file, but maybe to a USB drive or some other local storage on site, to a D drive. And I'm going to put it in a folder, test1, data.csv, everything looks good, and then I'll do the exact same process in that for loop. But I can't tell you how many times where I've been developing a program, writing it around, and I get a nice file structure. I take some test data, and then I realize that I've accidentally been overwriting all of my test data because I forgot to change the file name between runs of a test. So hopefully I'm not the only person who's done that. I don't think I am. But there are some tips around that too. One thing that I like to do is use the time library within Python and use this strftime function, which is used to convert these string characters over on the right into time files. So as long as you run this one line of a new file name every time before you have a test, then you can really easily tag your data. Of course, that's not super ideal because then you have to remember exactly what time you took the data you wanted, down to the sub-seconds if you really want to get that detailed. But this is at least a handy tip to use if you are looking for a better way to organize your files in your local storage. We're also going to talk a little bit later on about some ways to get around using local file storage as well. One of those ways to get around managing your own local file storage is to let a program do it for you with some dedicated local software control. Now, by dedicated here, I mean software dedicated for test and measurement control. So not writing your own program and not any generic software, but software that's made for controlling instruments. And the piece of software I'm going to highlight here is Keithley's Kickstart bench instrument control software. Now, it's not to say that there's the only one. There's quite a lot of software out there for controlling bench instruments. but I do think Kickstart is a great one to use. And generally all of them share some of the same core features, like being able to control all the settings of an instrument through a nice user interface, and really easily store data after you've taken it. One thing that's nice about Kickstart is if we look at this export data panel that it has a number of different settings for exporting data as you are taking it. So for example, you may be able to hopefully see right in the middle there that checkbox automatically export new runs. And then you can specify custom data paths of where you're going to store that data. So this is something that Kickstart does really well. You've got flags in there for your file names so that you can specify things as much or as little as you want when storing new data for a run. And other software, dedicated instrument control software, certainly does have other options here. But the key thing to keep in mind here is that for remote control, you should be looking at dedicated software and what's out there from your instrument manufacturer to help you be able to take that data. In general, these things are great for quick control and sometimes really even advanced control, as well as data logging for long-term tests, things like that. If you start getting into really custom needs or really complicated tests, oftentimes you're going to have to go down the route of writing your own code. But the dedicated instrument control software is getting better all the time, and there's a lot of huge improvements. You can do some really complicated things with it now. Okay, and another trick that we're going to now, which is instrument-to-instrument control. Now, this, generally speaking, is not very common, having a piece of test instrumentation be able to control other pieces of test equipment. But it is something I want to highlight. It's a great trick if you have the capability. What you need is a Keithley TSP compatible instrument in order to be able to do these two tricks that I'm talking about here. If you don't know what they are, you can find a list of them when you download the slide deck for this presentation. There's a list at the back of the slide deck. And there's two aspects of this capability that I want to talk about. The one is called Tsp Link. And again, this is only for Keithley made TSP compatible instruments. But what it allows you to do is create this mainframeless network by daisy chaining instruments together onto this network. It's sort of like they're creating their own LAN network. And you can see a code example down at the bottom to see just how really simple this is, where when you write code and write programmatically interface with the instruments, you just address them by a node number. So you can say node 1, we're setting an output, and then you just access the data from node 2 directly. So what this really allows you to do, and where it's most commonly used, is you have your main controlling computer that you're actually typing into hooked up to one instrument in this network, and you're sending all commands through this instrument, and it's seamlessly relaying everything to whatever instrument those commands need to go to. So this is a great trick to use for accessing multiple different instruments, and also it can save time for manufacturing setups because the instruments can talk to each other without having to relay everything back to the computer. And so instead you can get formatted data, whatever data you want back from this entire network from that one instrument that's talking to all the other ones. Now, Tsp Link, that capability is great, but it's only for TSP compatible instruments. Again, there's that list at the back of the slide deck for all of them. But there's another capability called TSP Net for those TSP instruments that allows those instruments to control any LAN-enabled instrument. So here's an example that I've done before where I was using a Tektronix MSO5 oscilloscope to make some power converter measurements. But I was talking to one of our source measure units over there on the right. So what I was able to do is I connected that source measure unit up to the LAN network at the office, and hooked the oscilloscope up to the same network, and then just started talking to the oscilloscope from the source measure unit, and was able to send it commands, command the oscilloscope to do things, and ask the oscilloscope to report data back to the source measure unit. Then I was able to really only talk directly with that source measure unit while the entire test was being performed. So this is a great trick to use for controlling any LAN instrument and being able to really consolidate all of your data into one place. That's at least what I use it for most commonly. And another trick here on optimizing raw data. This trick should be helpful for those of you that are having to deal with a lot of data. If you're only doing 1 or 2 tests daily, you're not really doing long-term data logging, you don't have huge sets of data that you're having to deal with, this one might not be as terribly useful for you, but hopefully still interesting. And this has to do with how data is returned to you once you ask for it from the instrument. Most instruments have some ability to control how data is reported out, how they actually are sending the ones and zeros, the numbers, out to the controlling computer. And these commands are generally found in some area of the programmatic interface called format. So here, a couple commands in particular that I want to call out. The first one is Ascii precision, or the precision, the number of digits that are going to be returned to you when you ask for a number. So keep in mind that all test equipment has some resolution associated with it. For really, really accurate instruments, when you get like DMMs for calibration, those are 8.5 digits, which is in counting the half digit, that's just 9 digits that actually matter, that the instrument are sure those 9 digits are accurate. Everything beyond that, if we go on to 10, 11 digits, are really just going to be noise. They don't really have any fundamental meaning, any physical meaning. We shouldn't be basing decisions off of them. So keep that in mind if you're storing a lot of data or asking for a lot of data back, that a lot of it is probably just going to be garbage. When you think about a test equipment will happily return as many digits as it possibly can, 16, 32, depending on how the instrument is storing its numbers. So you might want to limit your ASCII precision when you're asking for data so you're not getting all of this extra junk that's not necessary and taking up storage space. You can save a lot of storage space actually, depending of course on how much data you're storing, just by trimming down those extra digits. Now, the other thing I wanted to talk about was storing data outside of the ASCII format. This is particularly relevant for speed, in fact, for manufacturing speed, but also can be an interesting way to store data. So if we look at what these lower commands return, you can see that if you want to actually be able to read the data yourself, then ASCII is definitely the way to go. You can see what that number is right there. But if you're only using your data to perform extra storage on it, and again, if speed is an important thing, you want to get data out as fast as possible, then you might think about using some binary format, like otherwise known as real 64 for 64 bits or real 32 for 32 bits. And you can see that those characters over there are really just gibberish. That's just what happens when you convert binary into ASCII characters. You wind up with all these weird looking things. But we can go in a little bit more and look at what that actual real 64 format looks like. You can look at the individual bits. Of course, you would never really work with data this way by looking at the individual bits. You would use some computer to be able to work that knows how to work with real 64 and that binary data. But it is interesting to know that you could actually go through and do this by hand. So here the red numbers there and highlighted red, the #0, are just the starting characters. So that's how your computer knows that a string of binary is coming out from the instrument. It's also how the instrument differentiates what it's sending out. And then we get into the actual real 64 format. So that's following those 64 bits. I'm not going to get into how the format actually works, but just suffice it to say, it is an efficient way to store and transmit large amounts of data. And with that, my portion of the presentation is over for right now, at least though. So I am going to hand it off to my good friend, Rick Coleman. Go ahead and take it away, Rick.
All right. Hi, everyone. This is Rick, and I'm going to continue our conversation about tips, tricks, and traps with data and instrumentation. I'm going to talk a little bit through ways to use the cloud to actually improve your experience around accessibility and sharing with your data. And the first tip I've got here is to use data streaming to create remote dashboards. Data streaming is essentially the ability to stream data from many different sources into a single dashboard, and then that dashboard is hosted such that you can access that dashboard from anywhere, and on any device, including phones and tablets, PCs, your computer at work, or your computer at home. So let's talk about the product that Tektronix actually offers in this area. It's called Initial State. And Initial State is essentially what's called an IoT data streaming and visualization system. And all that means is that it is a system that allows connectivity through the internet from all the different quote unquote things that are out there. And in our application, these things are typically measurement devices, but they could be single board computers or normal computers and laptops or cloud destinations in and of themselves. Basically, any connected device or software can send data to Initial State and even read data from controls inside of Initial State. So that's the big sort of headline here, that you can stream data to a dashboard and then view that dashboard from anywhere. And of course, in an increasingly shared and remote environment, this could be really important in order to monitor instrumentation or understand experiments that are going on, or see devices in the field and then how they are doing and what they're doing. With Initial State, you can stream data from any connected device with a simple REST API. You can create these real-time web dashboards, and they truly are real-time. You can pull them up directly in a browser and just watch it. It automatically updates, and it's very fast and easy to traverse, zoom, and pan these graphs. You can also trigger on critical thresholds. This means that in the tool, without any extra coding, you can set up triggers such that, let's pretend like a temperature goes over a specific threshold that you set. You can then automatically have the system send you a text or an email when that happens. And you define the logic and the parameters around that trigger, and then the system sends that trigger. And of course, this system is on 24/7, 365, so it is monitoring when you set it up, your data, even when you're not. Lastly, you can share and embed these dashboards anywhere. Of course, you can go to the Initial State tool and see all of your dashboards, which we'll cruise around in here in a second. But also, you can set these dashboards to be shareable so that other folks can see it. You can do it securely and just share it with certain people on your team, or you can open it up to sort of a public link, and so anyone with the link can see it. You can also embed these dashboards into your own systems or web interfaces, just with an iframe link that's copyable, much like a YouTube video or something like that. So the baseline of how this works is that it's an API. It's an ingestion API for all the disparate connected devices. And we also have built many example programs and SDKs in many of the platforms and languages that you see here, as well as others, so that you don't have to go down to the bare metal API. You can use our simple examples in LabVIEW, for instance, or our full-blown SDK in Python, for instance. Here's just a smattering of examples of some of the things. You can get very dense data. You can get nice imagery. One thing that we'll show is that the data is on these graphs is very fast to traverse. So you can zoom down to a couple of individual data points and quickly zoom out to the whole world. So let's just take a quick example. Let's just pretend like you have some type of test system that's running in an automated fashion, and you want to take some of the key values and statistics and boil them up into a remote interface so that you can see this from anywhere. All right, I'm going to go over here to a browser, to initialstate.com, which is the microsite around this product, and just sign into my account. Essentially, Initial State is a collection of dashboards that you create. Here's all of my dashboards, and I'm just going to create a new one, and we'll call it Demo 5. Create this, and then we'll go to the dashboard. Now, here's an open dashboard. It's waiting on data. We haven't sent any data to it yet. So let's actually just do a couple of sample points. I'm actually going to go into the settings here and grab the API endpoint. This is just a test URL where you can send it data. Now, I could give you this URL and you could send data because it's truly cloudified, but I'll do this in the same browser. I'll say temp equals 72, and I hit enter there, and maybe we'll send a couple more just to see some things. So now here's a new graph that's been showing up as I've been sending those data points: temperature 72, 73, and 74. And this is all time-based based on when I sent it. With this, you can basically make different dashboards. You can lay out your items. I'm going to go ahead and just the key was temp, so I'm just going to make another one with that temp and let's make a gauge graph. Call it a thermometer because it's a temperature, and get out of there. So now we've made a little graph. Both of them are the same data. One is just an instantaneous read, and one is the line graph of the time-based history. So you can imagine how we could build up really nice dashboards like this. But I want to continue some demoing in here, but I want to talk about a trick first, and then I'm going to come back. So let's pop back over to the PowerPoint. And here's a trick that I want to talk about that is related to this dashboarding system. So we've talked a lot about the ways that you can send data to initial state based on, or from, I should say, programming languages and other types of systems. Well, there's some systems, including the Keithley data logger, the 6500s and 6510s, that have integration into initial state that does not require any code. It's actually just integrated into the instrument. And so if you can imagine, data logging is kind of a nice application for something like this, because just with a data logger connected to the internet with no PC in the middle, you can actually run long-running tests and have a web-based dashboard as your readout, as your report. So now you can do tests, environmental tests or halt-hoss tests or characterization tests, things that last hours, days, weeks. You can do that with a data logger and a remote dashboard, and now you don't have to go back and check in the lab. You can actually just see your dashboard whenever you'd like on any device. So let's actually set that up, and then let's go back into initial state a little bit. First, let's set up the 6510 to send data to initial state. Here I'm remoted into a Keithley 6510, and I've set up a scan to scan channel 110 and channel 115, which are both connected to a thermocouple continuously every half second. Normally I'd just hit start and it would start doing that scan every half second and saving. But instead, I'm going to go over to apps, click initial state, and say run. And this app is going to actually run that scan, but send the data directly up to initial state. Once I click OK, the relays are clicking here in the background. You may be able to hear them, but it's sampling 2 temperature channels every half second. So let's go back over to initial state and refresh our list, and we'll see that there's a new bucket called debuffer1. This is the new bucket that Keithley device created automatically, and now it's sending these 2 temperature values directly to this dashboard. And as we see, we can watch it in real time. There's new data chunking in. I can edit the dashboard as the data is coming in. It still continues to. I can make the dashboard look however I want and add new tiles. What I'm going to do is just kind of pull up a dashboard that I did before. So I'm going to go and import a view. And it's another demo that we've done earlier that just has a nicer dashboard. So this is, again, 2 channels, but there's all of these different mathematical derivations and different plots and different gauges. For instance, I've got a readout here that is using the expression engine. You can use simple math in order to convert the number to Fahrenheit and actually add the degree F. So there's some string manipulation capability. So all of this whole dashboard here is just based off the 2 temperature samples that are coming in. And as you can see, that the dashboard is updating as we speak. Go back up to this data bucket. We're making it better and better as we go. Let's add some triggers. So let's pretend like we don't want channel 110 to go above 50, or that'd be bad. And we need to send ourselves an email. And let's just say bad in the email, and maybe insert the URL to this dashboard so that directly out of the email you can click and go right to the dashboard. Let's add a text too with the same thing. just so I'm sure I'll get it. And let's say create. So now I've created a single trigger with 2 different notices going to 2 different destinations. I could put my whole team on there. Another aspect of this data collection is that I can share it. So I can share it by email with a specific person, or I can share this publicly and just get a shortened link and send this out to anyone, or embed this link in a web interface. So here you can see how initial state and instrumentation and other IoT devices or other devices that are connected can all be configured and programmed to send data to a remote location, and then you can monitor, trigger, and share from that remote location your dashboard that you need to look at. Let's go back to the slides. We're going to switch gears a little bit and talk about scopes. So one of the big traps that I see a lot of folks that I talk to, they don't have a great system for saving data from their scopes. They're using USB sticks, screenshots, email. I've seen a lot of people that just take a picture of the front of the screen with their smartphone and send that in an email. Well, that's not the greatest way to share data, especially if you want to share data that's more rich and doesn't squash all the precision like a screenshot does. So what we've introduced is a system called TechDrive. TechDrive is a cloud-based file system that is connected directly to Scopes, TechScope, which is the offline scope software, as well as a browser interface where you can check out your own files. It's supported now on the 5 and 6 series, as well as 4 series coming soon. That should be out in early Q2. It also is integrated into TechScope, like I said. So TechDrive is basically a Dropbox or Google Drive-like experience, but specifically meant for test and measurement applications. So let's imagine that in TechDrive, user 1, 2, and 3 all create a folder, and that folder is a shared folder among them. Let's say that user 1 saves something from the scope. You're directly on the scope, you save something called currentspike.tss. User 2 can open that waveform directly inside of TechDrive and take a look on any device. It leverages some of the same graphing technology that you just saw in the initial state technologies. And then let's say user 3, again in another location, can quickly download currentspike into TechScope and analyze and measure with the full glory of all the data, just like as if he was on the scope. Everything between user 1, 2, and 3 is automatic, doesn't require USB sticks, it's no email, no screenshots, and it's the full data. It's not just a picture of the data. Furthermore, there's a full, well-documented API for TechDrive. So you can use the platform of TechDrive under your automation. We deliver Python, LabVIEW, MATLAB code so that in your test setups, you can send and receive data from TechDrive instead of some type of local database or on-site database. Here, once you put something in TechDrive, instead of a test data repo or something like that, you actually unlock all this capability of being able to have secure anywhere access, analyze it on any device, share it across teams and geographies and partners. You future-proof your data because as new capabilities are added to TechDrive, you'll be able to take advantage of those just by the mere fact that your data exists inside of TechDrive. So if you look at TechDrive, and we're going to jump in and look at a demo, but essentially you've got secure anywhere access to your data. You can save and recall directly on scopes and inside of different software like TechScope. You can inspect and analyze. We'll show some of the graphing technology where waveforms can directly be shown in TechDrive. And of course, the main idea here is that you can collaborate. You can set sharing on individual files and folders. You can share securely with your team or even just yourself at different locations and on different devices. And with this web service API first approach to building TechDrive, you can really add this dynamic file system on top of any automation in any language fairly quickly and fairly easily. Let's get out and go check it out. All right, gone out to a browser and I've gone to drive.techcloud.com and it's redirected me to this authorization page. Just going to quickly sign back in. And Tech Drive, as you'll see, is a lot like an internet or cloud-based file system. Here's some recent files that I've worked on. Here's my main root directory. Here's some files that have been shared with me. If you look at, this is files and folders. If you right-click on a folder and say share, you can see how you manage sharing settings. This folder happens to be shared with 3 other people besides me. So, of course, anytime a new file goes into this folder, it's automatically shared with all these people, and presumably these folks are on my team or we are in a partnership in some fashion. This browser-based technology here is nice for organizing and moving things and adding files and downloading and searching and generally managing your files. But what makes this really powerful is a couple of things. Number one, you can get data from instrumentation directly here from the instrumentation itself. And number two, there are analysis capabilities inside of Tech Drive where you can actually look at waveform files and session files directly in the browser without downloading it and without any other software involved. So I'm going to go over to an oscilloscope here, and I've got a test waveform, and I just want to show the onboarding procedure for Tech Drive because it's pretty neat. I'll go down to File Utilities and say Mount, and what I'm going to do is mount a new Tech Drive. This is in the latest firmware of 5 and 6 series. I'm going to tell it to auto disconnect once you power cycle and start connection. Now here, I'm just going to pull out my phone and do this. You won't be able to see it, but I'm just pointing my phone at that QR code. I'm clicking. It gave me this short code here, and I'm quickly putting that into the system. And just like that, activation successful. And now I have a new drive in my system. It's the same, it's the interface is the same as the local C drive, or if I had a USB drive in this. But whenever I save now to these dynamic folders, it's actually automatically saving to my cloud-based folder system, which in turn is automatically sharing with all the people that I have it shared with. And also I can then access these files from anywhere. And I'm saving it in the same way that I normally would onto the actual scope itself. So let's just do that really fast. Let's take advantage of this. I'm going to go save as a session. I'll browse to not the C drive, but my Tech Drive. And I'll just save it out into the main area. Say, okay, let's call it just so we know 1, 2, 3. Say save. So this is wrapping it up to a session and automatically uploaded it to Tech Drive. So now from anywhere, I'm in the same browser, but I could be on my phone or not on the same network. I'm going to go back to my files, and there's that file, tech00123, that we saved. Now what's really cool about this is, yes, I can go and share this, of course, with anybody I like, but also right in the browser, I can right-click, launch in waves or lines, and I'll just show you one of the visualizations here. So if you remember, this was like a cardiac signal. So there's our cardiac signal. We can zoom in close. We can traverse the data really fast. We can zoom out. We can drop down cursors and check out the distance from here to here, let's say. Change my unit down to micros. So it's 30, 40 microseconds apart. So there's a lot of power here. There's also an expression engine where you can write math against it. And over time, we'll add a lot of different measurements and capability to this graphing engine so that it's not just a visualization, but a real exploration of the data. Okay, the last thing I like to do is go back to the scope. We save this data in a nice dynamic cloud location, and it's really cool to think about if you want to recall this data on a different scope, in a different lab. If you share this data with someone else and they need to recall it to their scope. I'm just going to go ahead and go out to default setup just to show what it's like. So imagine this is a new scope, a different scope, someone else's scope. If I'd have saved that data on the local hard drive of the scope or even on a USB stick, it would have taken me a lot to share this data with another scope or another person. But since I saved it in Tech Drive, I can just recall, go to my Tech Drive, and of course, there's our Tech 123 session and hit recall. Downloads it and brings it in just like that. All right, let's head back to the presentation. So we've taken a tour of TechDrive, and there's lots more information on the Tektronix website at /software/TechDrive. I wanted to leave you with one last pretty cool trick. You can actually use TechDrive and the act on trigger capability of a scope to do some codeless automation. If you know about act on trigger, it's a trigger feature in which you can set up a trigger and set the scope to look for that trigger and then do an action when it finds it. So this is often used to hunt for an intermittent problem. You can set the scope to start acting on trigger and saving on TechDrive when it happens, and then leave the scope and go back to your office or wherever or home and watch that folder, and it will slowly fill up in a completely automated fashion, and you don't have to go back to the scope to get those files. You now have those files where you are. All right, I'll turn it back over to Brad. Thanks.
Thank you, Rick. Insightful as always. And that does bring us to the end of our presentation today. Hopefully everybody had fun. Maybe you even learned a couple things. We have just finished talking about sharing test data across the bench and into the cloud. We walked through several different tips, tricks, and traps associated with that. And we'll now move into the Q&A portion of today's presentation. So if you haven't already, do be sure to think of a question, type it into the Q&A box. Also take advantage of the resources to download some reading material for later. And on your way out, do be sure to fill out the survey. Those survey answers really do help us create better presentations for next time. All right, now just give me a second here to switch over into the Q&A mode.